Alright, let's see this. Minimum operations to make all array values 1. You're given a zero index array, nums, consisting of positive integers. Okay, you can do the following operations on the array any number of times. Select an index I such that I is between 0 and n minus 1 inclusive. No, inclusive of 0, not exclusive of n minus 1. So not the last index, and replace either nums. Okay, swap placement. Ooh, replace either nums or num plus 1 with their GCD value. So not swap. Return the minimum number of operations to make all elements of num equal to 1. If impossible, return -1. So it would be impossible if like the whole array had like 2s or something like that. So because their GCD would be just that value, if that value is not 1. Okay. Yep. The GCD of two integers is the greatest common divisor of the two numbers. So 2, 6, 3, 4. So the GCD of 2, 6 would be 2. So you could make the 6 into a 2 in theory. GCD of 2, 3 would be 1. So you can make both these into 1 at that point. GCD of 3, 4 would also be 1. So you need to make this into a 2. Then another operation, or 2 operations to make these into 1. And then one final operation to make the 1, 4 into 1. 2, 10, 6, 14. So the GCD is just going to be 2. Okay. So it's going to be impossible. Alright, so is it the case that it's just going to be interesting. So the GCD between 6 and 3 is 3. So I could make this 6 into a 2 or a 3. Didn't matter there. If I made it into 3, then that would take 2 steps in order for it to make it into. Wait, did I count this incorrectly? 2, 6. I did that wrong, huh? So I think I first needed to make the 3, 4 into a 1, 4. Yeah. And then the 6, 1 becomes a 1, 1. And then when I have a 1, I can. Okay. So if I can get any pair of adjacent values that give me a 1 from the GCD, then I can spread that 1 elsewhere. And here I can't ever get a GCD of 1 from any pair. So the next question would be, what's the worst case? How long in the worst case can you get 2 consecutive values to be GCD of 1? Okay, so notes. If a 1 appears at any value, all adjacent values, basically to all adjacent values, which becomes all values in the array. So what is the worst case to get a 1 to appear in the array? So here it's not possible if array has some common GCD. So for example, 2 GCD of all elements is 2. Some common non-1. Do, 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 do. 210 is 5. 10.6 is 2. No, 210 is 2. 10.6 is 2. 614 is 2. So how would I construct it such that it would take like 2 operations to make a GCD of 1? So maybe if it was like 2, 6, well 263 is obviously not it, huh? Well, what if it was just 263? So 263 would mean that 23 becomes 213, and then onwards from there. And then like the 233 could also become 213. So here, the 6 was the only thing that could become a 1. And the 6 took 2 steps to make it into a 1. 6 took 2 steps to make it into a 1. So how would it make it? How would it be to make it into like 3 steps to become a 1? I think that would probably mean I need 4 items, like 2, 6, 18, 2, 6, 18, 3 maybe? 6, 18, 3. Would this require 3 steps? Kinda. It'd be like 2, 2, 2, 18, 3, 2, 2, 2, 3, 2, 2, 1, 3. So it does require 3 steps to get something to become a 1. 2, yeah, 2, like 2, 3, 3 or 2, 3, 3, 3. Yeah, that requires 3 steps there. Hmm. 18 becomes 3 or 18 becomes 6. I mean, you probably always prefer the smaller number, so if it's between 18 becoming 6 or 3, it probably should become 3. But then should you go make 6 into a 2 or 18 to a 6? Kind of, what is the default best first step? Default best first step. Less factors. 18 also has less factors. 6 becomes a 2, gets rid of factor 3 and 2. No, 3 and 3. It's not possible when there's a GC common to everything. So the operator, right? The GC is only non-1. The GC is only non-1 when they're relatively prime, that they don't have any common factors. But if they're not relatively prime, then they do have a common factor, and the value becomes the common factor. Or the value, one of the two values becomes exactly the common factors involved. So and the other common factor was another 6, so let's say it's 12. So the greatest common divisor here is 6. So it'd be a change, it becomes 612. Getting rid of the factor of 5, or it could become 36. Getting rid of the factor of 2. So if C is common GCF, greatest common factor of A and B, then operation converts A, B to AC, or converts AB to AC or BC. Common factors. Do greatest common factor. Do the operation any number of times. Alright, so if I say A is, let's say the common factor is K, Kx, B is Ky, where X and Y are relatively prime, then AB becomes like, AB becomes X, X, Ky, X comma Ky, or Y comma Kx. The common factor exists for one of the two still afterwards. It would take 2 steps to remove the common factor from both. Take 2 steps to remove the common factor from both. Wait, is that right? Shouldn't actually be able to remove common factors like that. Let me think about that. Because like 2, 10, 6, 14, you can't actually remove the 2 from 2, 10. No, so AB becomes like the greatest common factor would be K. So it'd be K, Kx, or K, Ky. And from there you get to KK. Yeah, so you don't actually become 1 there. So you can remove the relatively prime factors within any adjacent pair. Relatively prime factors. I can solve maybe the trivial case first, like if I can detect there's a common factor in all nums. if I can detect the relative and the common factor in all nums. Seems simple enough. I don't think I know how to do it though. Or not know how to do it efficiently. 2, 10, 6, 14. I wonder if the order matters. Almost certain the order matters. Yeah, order matters. Like something like this. That took 3 steps. It would take 1 step to get a 1 if the 2 and 3 were adjacent at the start. We were adjacent to start, so I mean, you can maybe start by assuming that all my array has some commonality, some non-zero, non-one factor between each adjacent element. Otherwise, it would just return n, where n is the length of the nums as the number of operations required, because then the first operation is to make the whatever adjacent pair that actually results in 1, 2, 2, them being relatively prime numbers. That'd be the first operation, then you should spread that 1 on to the other indices of the array. So it'd be trivial case exists a consecutive pair of values that are relatively prime. Return n. I guess that's the first thing. And then how to handle an array where all consecutive pairs are not relatively prime. So all consecutive pairs have some common factor. All consecutive pairs have some common factor. So you can make one of the pair become the common factor and the remaining relative prime factor, which could be 1, I guess, if both values are the same, or if one value is a multiple of the other value. So if both values are, say, if a equals b, or a equals k times b, then result is a. So you can't really change it if it's the same, like 2, 2, 3, 3 in the array, it just becomes 3, 3. Or if it's a multiple, 3, 6, then becomes 3, 3. So I guess the next thing is if it's not multiple. So yeah. So if it's like k, x, k, y, you can either keep, you either remove, keep the k, remove the x, or remove the y. Okay, so let's do this. 2, 2 times 3, 2 times 3 times 3, 3. So I'm thinking about this example here. 2, 6, 18, 3. So with one operation, I can remove 2 factors here. With another operation, I can remove a factor here. I wonder. Like 2, 3, I know that that's relatively prime numbers. When I get 2, 3, I know that's relatively prime numbers. So 2, 3, 3, 2, 2, 3. If I work from here, I can only remove the 2, or I can only make this into a 2. If I work going this way, I can only make it into a 3. I wonder if there was like multiple ways of like getting wrong, or setup where there's like multiple possible things to do. Like if this was, let's say, 15, so this is 3 times 5. So this would be 3 times 5 here. So 3 times 5, 2, 3, 3, you make this into a 3. Yeah, and you need another step here, I think. So 3, 6, you make that into a 2. On 3, 6, you can't make that into 2, can you? Greatest common factor between 3 and 6. You have to make that into a 3, I think. Oh no, I was thinking the other way around. 2 and 2, 3, make that into a 2. Yeah, and then you'd need another step here. We have 2, 2, 3, 3. Well, no, actually. That's not right. You just need to make one of them into a 1, and then you have a 1 here, and then 1 and 15 is 1. So I think this should be 3 steps still. Yeah, this is still 3 steps. 3 to get a 1, and then to expand out the 1 would be another 3, so it'd be 6 steps total. 6 steps total. Yeah, 6. Wait, no, that's wrong. No, that's right. Okay, yeah, 6. So, yeah, can't really mess around with changing the 3 times 5 into a 3. Has to be like changing 18 into a 3, or changing the 6 into a 2 is the first step. How to form a 1. Yeah, question is not really how to make all array elements 1, it's just how to make 1. How to get a single element into a 1. How to get a single element into a 1. So reversing that, that means how to get two adjacent elements to be relatively prime, sharing no common factors. How to get two adjacent elements to be relatively prime, sharing no common factors. So you can't really make this into relatively prime because there's always going to be a common factor. Unless somehow you can make this into a 3. And you can make it into a 3 if you can somehow remove a factor of 2 from the adjacent one. And 18 has a 2, so you can remove the 2 as long as 15 has no common factor of 2. So 18 becomes something that doesn't have a 2. Then that makes this thing not have a 2. That makes whatever remains not have a 2. I think this is actually the reverse. I think maybe this is removing a 3. Yeah, it's 2, 6, 18, 15. So logically, in order for these to be relatively prime, 6 needs to get rid of its 2. In order for 6 to get rid of its 2, 18 must have something that doesn't have a 2. And for 18 to not have a 2, it needs to go to 15 to get rid of its 2. And 18 and 15 do get rid of a 2, so 18 becomes 3. And then that leads to 6 becoming 3, which gets rid of its 2, and then the 2, 3 becomes a 1, right? And then the 1 spreads. Okay. And then if I do that in reverse, if I say that 15 and 18, they have 3 both, and then that means I need to get rid of the 3 from the 18, so I look at the 6, but it also has a 3. So it needs to get rid of the 3 from the 6, so it looks at the 2 and says, yeah, 2 doesn't have a 3, so therefore this can become 2, 2, 18, 15. That gets rid of the 3 from the 6, and then I can get rid of the 3 from 18. 2, 2, 2, 15. And then the 2 and the 15 no longer have any common factors. So that takes 3 steps. So 3 steps to get the 1. So is it a process of elimination? Is it a process of elimination? So 2, 6, 3, 4. So 2 and 6 have common 2. So 6 and 3 have common 2. No, have no common 2, so therefore you go 2, 3, 3. And then you can make this into 2, 1. Is that the best approach? I mean, it's either going to go left to right or right to left, right? Because if at any point you can go left to right or right to left, I guess the complication would be if there's multiple factors still in play, maybe. Pretty big numbers, only 50. there's multiple factors in play. So you start with the first number. You see the common factor between that and the next number. So let's say you start with the first number and say it's k. The next number is kx. And then the next number is ky. Let's say it's kxy. And then the next number, actually let's say the first number is abx, the next number is aby, and the next number is abxyz. And then the next number is, let's say, ayz. So in theory, you can't actually get to 1 here. Let's say the next number is like bxy, yeah, bxy. So you can get rid of so in order for abx and aby to be relatively prime, you need to get rid of the ab from aby, because you won't be able to get rid of ab from abx. There's no neighbors there. In order to get rid of the ab from aby, you need to go to the next one and say, can you get rid of it? And you can't. So you go to the next one and say, can you get rid of the AB? And you can get rid of the B there. And you go to the next one, can you get rid of the AB? And you can get rid of the A. So here it would take like 1 step to get rid of the B, and then 1 step to get rid of the A, and then 1 step to transfer it. Oh boy. Yeah, I'm not thinking about this correctly, I don't think. Or I'm not thinking about this maybe in a way that makes it easy to solve. Turn the minimum number operations. Each operation will remove, assuming it's not impossible or not all the same, maybe each operation needs to remove some factor until you can get to relatively prime, until you have no shared factor between adjacent elements. Each operation removes factors. Each operation removes factors. 2, 6, 3, 4. Two, 6, 3, 4. So you could start off with 3, 4. Oh, actually, wait, did I do that wrong? Yeah, you need to start with 3, 4 because that's actually leading to 1, right? If you do go with the 2, 2, 3, 4. No, if you do go with the 2, 3, 3, 4, 2, and then 2, 1, 3, 4. That gives you 2 steps to get to the 1. In theory, you could have just done 3, 4 and got on the 1. Is there a quick way to determine how many steps it would take to get 2 adjacent values to become 1? Two, 3, 3. 2, 2, 3, 2 times 2, 2, 3, 3. Probably start off by maybe finding the GCF between each adjacent thing. I think that's probably a decent starting point. Yeah, it's probably fine. And if I see a 1, then I just return immediately. Is there just a GCF function in Python, I think? It's a GCD, greatest common factor divisor, sure. For every index in range n-1, n is the length of the nums, n-1 because I'm going to be accessing index in x plus 1. GCFs dot append GCD, greatest common divisor, between nums at index and nums at index plus 1. I guess I want to keep the value there. If the GCF is equal to 1, then return n. Otherwise, do GCFs to append okay. So that works for this one, because it's just dummy. Okay. So GCF here was 2, 2, 2. 2 between 10, 2, 2 between the 6, 10, 2 between the 6, 14, 2 between the 2, 6, 6 between the 6, 18, 3 between 18, 15. Okay. I wonder if I can just chain the GCFs. Is it possible? Can I chain the GCFs calculation? I feel like this should probably be something akin to a one-pass solution. So probably not good to chain it because that's probably going to be like n squared. That's assuming that even the GCF calculation is an O of 1 operation, which it generally isn't, I want to say. I think GCF is log n, or n is or log k, where k is the size of the value. Huh. Do, do, do. Okay, so if I see this, 2, 6, 3 are the adjacent GCFs. Obviously, it's not going to be a trivial case. There's no 1. So what's to prevent me from doing another pass of the GCF on these? What would that mean? What would that mean? Okay, actually I want to do this. I would want to always have the printout of the GCFs here. So the first case is 2, 3, 1. 2, 3, 1. So here it's impossible because there's never a point where doing the GCFs, the greatest common factors, yeah. Yeah, so what this is saying is I can replace any of these things with one of these, right? I can place the 18, 15 with a 3, or I can place the 6 and 18 with a 6, or I can place the 2 and 6 with a 2. So these are possible replacement values for my values in my array. Which probably should have been something I understood pretty quickly from the reading the problem, but now is when I'm actually realizing it. So obviously a 1 is ideal. Something that's something that is never. All these will always. Interesting. So even if I do the GCF of these, it's always going to be 2s. So if I replace everything with some combination of these, then the next iteration is find the GCF of these, right? GCF between 2 and 6, GCF between 6 and 3. So that's 2 and 3. And then GCF between 2 and 3 is 1. Interesting. Okay, so if I did the GCF between these, yeah, okay, yeah. So I get 2 and 3, and then I get a 1. That means there's 2 steps, or 1, 2, that means 3 steps, okay. So I just need to do this a bunch of times until I get the same array or a 1 in the array. Wonder if that's fast enough. I don't think that's very fast. But I mean, there's not that many nums, I guess. So it's probably pretty fast. Okay. So I think I can say GCFs is that. So I can probably do a while loop, to be honest. No, can I? So if there's ever a case where all nums are divisible by the GCF, by the minimum of GCF, then then I can return negative 1. All nums are the same. All nums are divisible by the same. Can I... So what happens... I think, what happens if it's like 2, 3, and 2, 5? 2, 3 times 2, 5. So if my array was 6 and 10, greatest common factor there is 2. So it's not always divisible by the same value. If I reduce it to what exactly? What if it was 2, what was it? 12, 6. So so the GCF here would be 6, 2, which becomes a 2. So that I need to actually do all the way to 2 in order to me figure out that that's not possible. I don't know. Maybe, alright, I'm gonna do the stupider version and then maybe try optimize. So just the dumb version would be changing it until they're all the same. So like the min is equal to the max maybe. Maybe I can track that. That probably might be okay. Yeah. Actually. Is it actually O of n or is it any faster? Yeah. Okay, so let's think about this. So I think this would be while true maybe, because I want to do this multiple times. And let's say length is equal to the, let's say I have my current array is going to be nums. Length is the length of nums, or length of the array, for every index in the range of n minus 1, or length minus 1. And let's say my next array is the GCFs. So yeah, GCF between two values is going to be GCD of nums, or array index plus 1. If this GCF equals 1, then return return what? Okay, I think I need a counter here. So I think I return the length of nums plus count. Length of nums plus count. Where count increments each time I do this thing. So if in the first pass of calculating adjacent GCFs, or GCF from adjacent values, I see a 1 somewhere, and count is initially 0, so that means it's a default of n operations, and then if it's in the second pass, then it'd be plus 1. Yeah, I think that's right. And then if it's not, then I append this. And then after I do the whole loop, then I'll replace the array reference to the next array reference. Replace the array reference with the next array. And then I need to do the sanity check that all the values are not the same. Or somehow if all the values are some multiple. I could store min and max. Could store min and max. I could just do like if the value differs from the previous value, just a boolean. What's the simplest way? What's the simplest way? I guess the simplest way would be min and max is just too. If min equals max, I guess no, this is not going to work if the next array becomes just a single value. So I guess while next array, or while array is not, while there is an array, and this thing eventually becomes, actually what if I just did that, right? Actually if the array is just 1, because eventually 2, 2 becomes 2, 2, then the length is 2, index is 0, 2, 2 is going to be 2, and then it's going to be a 1 length of 2, and then it returns negative. I think actually that's fine. It does go kind of long actually, because if it has like 1,000 twos, then the next pass is going to be 999 twos, 998 twos, 997 twos. So I don't want to just have it return based on getting to 0 length. It's just too long. Yep. So I think I just store a min and max probably. Either store min and max or a boolean that compares the previous value and the current value. Okay. Same, let's say all same is initially assumed to be true. Actually, let's say it's assumed to be false, assumed to be true, if all same. Okay, actually, that's fine. If all same and I need to compare the current with the last. If all same, index greater than 1, and that's kind of stupid. Guess what is the best way of doing this? Fine. If all same and there is something in the next array, and the current GCF doesn't equal the last item in next array, then all same becomes false. And then here I can also return if all same is true. return -1. Okay. Was this the best way of doing this? Probably not. Not by a long shot. But there were the GCFs. I think I made that into the array and next array. Count is necessary. Yep. See how this does. See what errors it has. 1 1. Oh. 1 1 just should return 0, right? Huh. That's a trivial case I definitely didn't consider. So in theory, ugh, I think I might need to just handle this trivial case or this edge case separately. So if the min and max is equal to 1, okay, maybe I'll say min value is the min of nums. Max value is equal to the max of nums. If min value, what's the deal here? If 1 equals min value and 1 equals max value, return 0. Else if 1 equals min value or 1 equals max value, return n. Okay. You access variable n. Oh, whoops. Definitely should have defined it before I used it in such a manner. Oh my lord. What a stumper. 1, 2. Oh my god, it's oh my god, I'm so bad. It's the number of things that need to become 1, right? Is that only on the first pass that this is an issue? I think maybe. Okay. Oh, wow. That's really bad. Okay, so let's say count ones is 0 for every value in nums. If that value is equal to 1, then count ones should increment. Return n if count ones is not 0. Return n minus the number of count ones. Okay, I think that's that might actually be closer to being correct. Yeah, so this should be 2 minus 1, 1, so that's 1. Okay. And if there's any 1s at all, then yeah. Oh, I'm so bad. I really need to be better at making these test cases before maybe compiling. Count ones is misspelled. Oh my gosh. Oh my god. Okay. guess it didn't matter to do any sort of optimization there. And the size of the array is, let's see, is this part 1? Yeah, the size of the array is whatever, right? It's like 50, so you could probably even do an n squared thing, and well, actually I did kind of do an n squared thing. Yeah, I wonder if this is actually optimized enough. If this was like n is, or the length of the array is like 5,000 or 10 to the fifth actually, so not 5,000, not 100,000. I mean, it's pretty fast. I want to say this is n log n kind of. So the number of passes, each pass is going to be n operations. Each operation is going to take log k to find the GCF between adjacents. And the worst case would be what? The worst case might be log k in terms of getting it down to 1. Because there can't actually be n layers to it where they're all different GCFs. They're all non-1 GCFs. So it's like, yeah, this thing feels like maybe an n log k times log k, something like that. All right. Oh, that was something. We'll see if tomorrow brings out the other one. Okay, so yeah. Okay, yeah. So summary is if an array of GCFs is created, then values in the array can be considered replacement values for the 2 values in the original array that were part of the consecutive pair it formed from. If any of those GCFs are 1, then should be able to convert neighboring cells to become 1, as GCF of 1x is 1. Logic can if none are 1, then create the GCF of the GCF array, kind of difference, and see if 1 exists in that array. The number of layers of GCS needed is the number of extra operations necessary before a 1 value appears in the original array. Once that is found, can comparatively can relatively quickly determine how many original operations were needed. Note that there are some edge cases where 1 appears in the original array, which probably is best handled outside of the main loop. Okay, so yeah, so this is handling the ones. If there's no ones, then this is handling the calculating of GCFs and layers of GCFs. Okay, and then time complexity, this gives me O of n log k, where n is the length of nums array, and k is the largest value in the array, or largest possible value. This is because this is due to the fact that the loop iterates over every value / index in the array, and actually I guess this is still O of n log n times log k times log k. O of n log, I guess that'd be log k times log k. Yeah, that's not the same as 2 log k. It's like iterates over and calculates GCF of v1, v2, which takes log k time. Also, the maximum number of layers to that should be logarithmic. So like, yeah, if you have some GCF array, the number of layers to get that GCF array to have a 1 in the worst case up here would probably be log k, something like that. To get that GCF array. Okay. Space complexity, this should be O of n, where n is the size of the array. Since GCF array will be 1 less in size each layer.